Hello and welcome to this manufacturing process technology part 2 module 8. We were talking about plasma systems and particularly concerned with the DC glow discharge system, where we already discussed about how this glow discharge is carried out inside a chamber with evacuation followed by the injection at a controlled rate of a bimolecular gas, and there by breaking down or reaching the breakdown field of the gas so that these following events could happen: dissociation, atomic ionization, molecular ionization, atomic excitation and molecular excitation. So we'd given details about what all these processes would typically mean, and then the question was how to sustain the plasma once the ions and electrons have been formulated within the chair. So as we see here, there is a DC source for doing this sustenance of the plasma, and the way that this sustenance would happen is that typically when the DC source applies a potential and makes one of the electrodes positively charged on anode, the other one cathode. So obviously the electrons would now start going towards the positive electrode as shown by these bright blue balls, and the dull blue balls, which are actually bigger in size, are the ions. They are going to go towards the cathode because they are cations, and they can actually go and bombard at a certain velocity, which is also dependent on the biasing voltage that has been provided to carry these along the plates. And the moment there is a bombardment of this heavy ions onto the metallic cathode, there is a production of secondary electrons as can be seen here, and so therefore the cationic hit would result in the generation of secondary electrons, and the electrons again would retain a momentum in the opposite direction because obviously they are being pulled by the field towards the anode, okay, and so they rush back, and while rushing back they hit further neutral ions or neutral atoms which are available, or neutral molecules which are available in the chamber, and try to ionize them further. So basically the secondary electrons which are getting generated here create a sheath of plasma or sheath of ions and electrons very close by to the cathode plate, and this kind of makes sure that the plasma is sustained. Okay, so more ions which are created here would again rush towards the negative voltage or the negative electrode of the cathode, and again produce more secondaries, and this secondary would again sort of induce more ionization effect near the cathodic region. So there is a sheath of cations which would come because of this secondary electron release process and bombardment near the cathode to the otherwise neutral gas molecules, which would turn into becoming ions, and these ions would again sort of in a chain reaction manner would again pump out more electrons. So this leads to the sustenance of the plasma, even though the high voltage source has been excluded from the circuitry, and the power which is consumed by this DC volt DC voltage source is really the power which is needed for sustaining the activity of the plasma for a long amount of time. So that's how DC glow discharge takes place. Let's look at what are the kind of zones which are formulated in such a glow discharge. So typically in a glow discharge tube you have some portions which are very bright, okay, as you can see in here by the dark blue glow, and some portions near the electrodes, for example the cathode and the anode, which are exceptionally dark, and then also some dark fringes or dark spaces in between this bright zone. And based on that, these different areas are characterized or are as named or classified as the Crookes dark space, which is typically at the cathode. Obviously the electrons which are coming out of the cathode are highly energized, and they are responsible for creating ions rather than moderate energy species. As I told you earlier, that the moderate energy species, because of atomic or molecular excitation, are really responsible for creating the brightness, the glow, because there is a short lasting electron in a higher state which generally jumps back and creates some kind of a discharge or light discharge or photonic discharge because of change of state. So and from a excited state to the ground state, there is a transition process which is accompanied by this glow discharge. So, the Crookes dark space is basically because all the available species are now in ionic state close to the cathode, which is also responsible for the sustenance that I had sort of spoken in the last slide. On the other side, on the anodic side, anode really is an electron sink. So, whatever comes in is actually pulled in, and there is no scope for any positive ion, because the positive ions are all repelled back into towards the cathode region. And so, therefore, you have a dark space here, the anodic dark space, and in between there is obviously an area where the momentum of the electrons which are going to create additional secondaries are such that they would knock off the electrons from the atomic species rather than mildly or moderately excite them. So, there is a region where this knocking off tendency would happen, where the electron energy is completely absorbed, beyond which the electron again starts to go by, and so therefore, there is a space which is completely filled with ionized species again in between the two cathodes and anodes, and the remaining area is a glowing region where there are these mild energy species or mild energy electrons which would atomically excite the molecules which are present in the plasma chamber. So, you have a reduction in electron density on one side, space used for microsystems and microelectronic fabrication normally, which is the cathode side. You have electrons gained, electrons that have gained sufficient energy to primarily ionize the gas in the molecule, creating a Faraday's dark space, and then you have a high kinetic energy of the electrons and anode acting as an electron sink responsible for the anodic dark space, and the glow comes normally from the moderate energy species in a plasma source. So, incidentally, our focus also would be on this Crookes dark space, which is used mostly for microelectronic fabrication, because there are ions and there is bombardment of the ions. So, if there is a material which is kept there, there would be a influence over the material by the ions striking the material at a certain velocity, and you could actually tailor the pressure and power regimes of the plasma in a manner so that the mean free path can be controlled, and therefore, you can have a case where there is a high impact which dislodges the material, or another case a very low impact with just some kind of a surface chemical reaction on the surface of the substrate which is kept in such a space. So, having said that, let us look at the potential problem which would happen in such a glow discharge, particularly when we are using insulating materials. And as I had earlier illustrated, that when we are talking about a DC glow discharge, obviously the cathode and anode polarities do not change. It is a direct current signal that is being fed into the system. And so, think of it that if I had an insulating substrate on the cathode side, beyond a certain level of creation of let us say electrons, the sustenance part of the plasma becomes very difficult, because it may not generate enough secondaries to produce that sheath of cations, which is really the driving force behind the sustenance of the plasma. So, therefore, people have looked into alternately engineered systems where this DC effect does not have to bother, even though there is an insulating substrate on one of the electrode. And one of the initiatives that have been taken is towards this radio frequency discharge or an RF discharge system. So, typically there is a radio frequency signal which is now sent into the plates, and there is a blocking capacitor which kind of filters all the DC component, only generating the sinusoidal signal to these plates. And obviously there is something called an impedance matching network, which I am just coming in a little bit why it is needed, and then there is a bias voltage which is given here through an inductor coil. So, the way that this system works is that the blocking capacitor DC isolates the chamber, the inductor I is used to protect the supply V, which would be used later on for the purpose of giving a bias to the LC circuit, as suggested here in this particular drawing, and using basically a radio frequency power to actuate the plasma process in this particular chamber. So, let us look at why it is needed to balance the resistance of the source, so that there would be maximum power transfer between the source and the electrode. So, let us suppose in a conventional case, if there is a source resistance which is associated with any power source and a load resistance RL, there is a way to sort of formulate a maximum power transmission or transfer condition from the source voltage to the load resistor, and let us look at how we do it. So, supposing we had a current I in the particular circuit. So, I basically can be written simply by Kirchhoff's law as V divided by Rs plus RL, and power, as we know, across the load resistor is nothing but I square RL. So, you have square of V Rs plus RL whole square times of RL. In other words, I can actually write this down further as Rs square plus RL square plus twice RL Rs, and divide the whole thing by RL, which brings us to a sort of a condition, namely V square by Rs square by RL plus twice Rs. So, in order to maximize the power, the resistance here or the denominator here needs to be minimized, and for minimization would simply sort of differentiate this expression Rs square by RL plus twice Rs with respect to RL, and this would yield typically Rs square by RL square with a minus sign plus 1, okay, and then equate this to 0. So, therefore, the condition for the maximum power transfer to happen would really be that the source and the load resistors are equal to each other. So, obviously, if I do a second derivative here with respect to RL, we are able to see that what results is actually a positive term 2Rs square by RL cube, which shows that we are treating a minima, okay, or we are dealing with a minimum point. So, for the minimization of the denominator term here, the power obviously is the highest, and the power transfer, which is the highest power transfer, takes place for this condition Rs equal to plus minus RL. So, therefore, let us come back to the plasma source as we was explaining and try to see what we are meaning here. So, this set of network is a sort of a matching network which would be able to sustain the maximum power transfer between, let us say, the RF source and the internal resistance that the source would have with respect to this variable load. You have to remember that there is a medium here which is a bimolecular gas, and then also it has a ionic discharge and electrons which are there, and the density is not in our control. So, therefore, the impedance that this capacitor plate set would occur to happen to offer to an AC signal or RF signal would be really varying. So, therefore, we need to keep changing the overall impedance in this whole region, so that this RL or the load resistance could be made always equal to the source resistance of the RF power right here for the maximum power transfer from the RF voltage source into the system. So, that is the reason why we have a impedance matching network, as you can see particularly here. I am just going to rub off all these different lines to sort of avoid any confusion. So, that is how you can think of the reason for having a impedance matching network. So, having said that, now let us look into another different aspect, that how this RF driven plasma really works out. So, let us look at what would be the sequence of events when ions and electrons are formulated within the plasma chamber. So, in one go, when let us say the first half of the cycle, this particular plate is positive, and let us say the other plate here is negative. So, obviously, the ions would start moving towards the cathode and the electrons would start moving towards the anode. And supposing we were to change the RF signal by reversing the polarity, so obviously the ions now would start moving towards the upper plate and electrons would move towards the lower plate, and this keeps on happening at a certain frequency. Okay. So, in one instance, for example, there is a electron moving up, ion moving down, another instance is the other way around, and this keeps on happening based on the frequency of the RF source that is being formulated. Now, there is a situation beyond a certain critical frequency, which is in the range of about 10,000 hertz or 10 kilohertz, where we can actually see that it's only the ions are too heavy, and so they are not able to follow the field anymore, as the electrons which are going to go to the plates. So therefore, the ions kind of confine themselves to the bulk of the plasma, whereas the electrons travel from end to end, making the plates relatively negatively charged with respect to the bulk of the plasma. So at RF frequency of greater than about 10,000 hertz or 10 kilohertz, this additional effect comes in where only the electrons move and create negative polarities on both the plates with respect to the bulk of the plasma, which actually has a bunch of different positive ions. Okay. So this is what is going to happen even if there is a pulsating signal. Okay. So the electrons are the ones which are moving and the ions do not move anymore because of the high level of the frequency. So having said that, now let us look at the a slightly different form of plasma, which is actually the magnetically enhanced plasma, and basically these are plasma systems which are supposed to produce one of the highest plasma density levels. Let us look at the basic principle. It is based on, again, the factor that there is a magnetic field associated with a circularly flowing current in a loop. So supposing there is a a chamber here, as you can see, and there is a evacuation process and also a gas release where a diatomic gas has been flown into a chamber, and supposing there is an RF coil which is surrounding this particular chamber, and at first instance what we do is create some kind of a spark to generate the plasma process. Okay. So at this instance what we are trying to do is that we have a Tesla coil right here which is going to generate a small spark and the spark would thereby ionize some of the gas molecules in the near vicinity of this Tesla coil, creating some ions and some electrons. At this instance, if we apply a current, let us say, in the coil around the chamber, there is obviously going to be a magnetic field associated with the direction of the current given by the Biot-Savart theorem, where because of the given by the right hand grip rule, where you can see that if supposing the current is going in a clockwise direction, the magnetic field would be always based on the direction of the thumb, and so there is going to be, if the current is from top to bottom, a magnetic field given in this particular direction. Okay, so the electrons and the ions which are again moving with respect to the medium around this place would obviously face certain forces, Lorentz forces, which are given by which are proportional to the charge, which are proportional also to the product between the velocity of the charge and the magnetic field, which is the ambient magnetic field generated by the coil. So supposing now if we add an additional constraint that this is an RF coil and therefore there is a change in the way that we are flowing the current. So in one instance the current is flowing, let us say, from the top here to the bottom, and in the other instance the other way around, the current starts from the bottom and goes all the way to the top. So obviously the magnetic field in this case would keep on oscillating. Okay. So in one case the magnetic field goes or points down, another case the magnetic field points up, and there are going to be different directional forces which are applied by the changing direction of the magnetic field. Remember, the force is actually proportional to V cross P, or velocity of the charge cross the magnetic field direction, and so if the field direction is reversed, the force would be reversed. So there is a critical situation where this frequency would generate a condition where the ions would start moving in circles, and mind you that if I wanted to calculate what is going to be the radius of such a circle, and if we assume, let us say, in one particular case that the velocity and the magnetic field are perfectly perpendicular to each other, sine 90 being 1. So we can have the Lorentz force F equal to the charge value Q times of VB, and the centrifugal force which is needed for some ion to keep at a certain radius with a mass m and velocity v is given by mv square by r. So, only when there are when these two forces get balanced to each other would be a condition when the ion would, or the mass of the ion would start executing a circular path of radius r. So, in this particular case the radius r then would be known by simply calculating the mv by qb, and if I want to look at the kind of magnitudes that this radius would have. So, obviously the charges on a ion and an electron are more or less similar, because if one electron is lost by the ion would at the most have +1 or 1 proton. Okay. But what is different though is the mass. So, the ion being much heavier in comparison to the electron would actually go at similar velocities for a higher radius. So, the ion's radius typically would be very high, whereas the electrons would have smaller radius, and this condition is a very strange condition, that the ion takes big loops or big circles and finds that many electrons in its path across this radial motion are actually executing small circular motions. So, they have more hits which would start ionizing the material, and there would be a high density plasma which would result from all this magnetically enhanced system of plasmas. So, in fact, this magnetically enhanced plasmas are known to be one of the highest plasma density levels that any system can offer. So, just like to take you through some of maybe a little bit classified information about how do you perform plasma assisted etching. And as we had already learned in wet etching case, that it is an act of engraving by means of which an agent eats away lines or surfaces left unprotected in different substrates. There is also something called an undercut, which we had found earlier in one of the modules, where we were talking about a lateral etch with respect to a vertical etch because of the homogeneity or the isotropicity of the etching process, and the extent of that undercut is really determinant of how anisotropic the etch would be. In fact, there is something called a etch anisotropy factor A, which is related to 1 minus lateral by vertical etch. In a case where RL and RV are equal to each other, this A becomes 0. So, it is completely homogeneous or isotropic, and if it is a case where there is more vertical in comparison to the lateral etching, it becomes more and more anisotropic, and you can think of this anisotropic etching process to be something which you'd earlier seen in the case of hydroxide etches, but in this case we would be talking mostly about plasma assisted etching processes. So, different plasma etching regimes have been classified based on the chamber pressure which is existent within plasma systems. Obviously, chamber pressure is an indication of how small or big would be the mean free path between the different ions. If the mean free path is higher, then there is a tendency of the ion to sort of go and bombard. So, we have now classified into 3 different kinds. One is the high pressure plasma etching system, which is typically a small few layers of chemical reaction of the species in the plasma with respect to the substrate surface. Reactive ion etching, where you have a physico-chemical kind of a behavior. So, there is some kind of a bombardment because of the biasing voltage of the plasma, and there is some kind of a chemical etching process which is existing in parallel to each other. And again the ion milling, which is at extremely low pressure, corresponding to about 10 to the power of -3 to -5 torrs, and this typically means bombardment and knockout of the atom. So, it is something like a very low mean free path, because of which high energy species can be bombarding the surface on a continuity, thus removing the material from the surface. So, that is how plasma assisted etching is classified. You can have different lateral etching regimes as shown here. All these have cases of lateral etching. This is, for example, a very good anisotropy isotropic etch, where AF is close to 1 and there is no lateral etch, which is there in only vertical etch. So, typically the etching would always be having an undercut, for which there is always a over design of the masking system. The etch mask is made in a way so that you can take care or accommodate for this undercutting action of the etchant that you are trying to develop. Okay. So, the following are the steps of the plasma etching process. So, there are high energy species and free radicals which are available in a plasma chamber as given by these species marked with stars. So, typically such free radicals would graze on the surface of the substrate and try to find out a zone where it would have dangling bonds, and they would try to get associated with some of the substrate atoms. So, if such an association is possible, it would take away now the atom as a gas phase, and it would get pumped out of the system. So, therefore, the reactive species of a plasma are able to take off the atom in this manner, and there are many such illustrations where either small chemical changes would happen on surfaces, or the atoms would go totally out by chemical reaction and then going into gas phase and getting pulled out of the plasma chamber, and based on that you again have the three different regimes of high pressure, moderate pressure and extremely low pressure of plasma etching. So, in this particular slide I would like to share some of the real results which came in one of the experiments when we were trying to do plasma etching, where we would actually take a PDMS surface and try to expose this surface to oxygen plasma, and there would be an immediate change in the surface groups because of the high pressure low power regime which you would consider here. So, there would be a conversion of the CH3 into OH of a polymer called PDMS, which we have been talking about in great details in the earlier slides, and this would result in the formation of hydrophilic OH based hydrophilic surfaces. Before treatment, the PDMS surface has a contact angle of about 109 degrees because of the abundance of these non-polar groups, or CH3 groups on the surface. But as soon as the surface treatment of oxygen plasma is done, there is a small layer, again because of the high pressure and low power regime, which gets formulated, and it is a chemical layer of SiOH on the surface, which results in lowering of the contact angle. So, if I were to actually plot the bond strength so basically the idea here is that if supposing I had two such layers of surfaces which I would bring in close proximity or hold in close proximity of each other for some time, there is going to be a tendency of H2O group to get generated and a irreversible bondage getting formulated between the Si on both the upper surface as well as lower surface. So, there is a silanol linkage which happens, SiO-Si linkage which happens at the behest of the water molecule which gets escaped from the intermediate region. So, the two surfaces which are now exposed to plasmas can be brought close to each other to have an irreversible linkage with respect to each other, and we were trying to test the bond strength of such a surface. So, we had in fact generated a test for this which is known as a blister test. I am just going to refer to this just a little bit later, but the idea here is that we found out that with the contact angle after the plasma exposure on a surface, there is a changeover of the bond strength as well, and it can be correlated to the density of the the SiOH or the silicon hydroxide groups on the surface as a function of different parameters of the plasma, which would eventually result in a variable bond strength. And what we see is that if the contact angle is below a certain value, the bond strength is going to be sort of maximum in this particular illustration. The way we did the bond strength studies are through the standardized blister test. So, we generate a pattern and with microfabrication generate a small blister pocket and connect it through compressed air, and under a microscope we shoot in the compressed air and try to see what is the expansion of this blister. And there is sort of a instance when you can see the surface is getting separated under the microscope, and that is the pressure corresponding to which the bond strength fails or the bond fails between the two surfaces that are in question. So, this way you can find out that due to the oxygen plasma exposure, there is a surface transformation, chemical surface transformation limited to only a few layers of the surface. Okay. And so, there are various schemes to point this out. One scheme through a UV and O2 plasma, you have a CH2OH which changes into again a dangling bond here, and there is a OH already existing through the water vapor in the plasma chamber, which comes and sits on the top of this dangling bond. Another scheme, again, you have several different intermediate steps here as illustrated to finally formulate this SiO H at the top of such a surface. So the many such schemes which have been studied earlier by people, but the exact window of operation of in terms of the pressure and the power of the plasma system would come out by this contact angle analysis, which is a sort of an universal scale to gauge whether you would get good bonding strength between the different surfaces which are participating in this particular process. There are many such phenomena, many other phenomena which happen because of the exposure to oxygen plasma. One of them is chain scission, because of which there is a molecular reorientation and there is always a formation of a sort of a crack on the surface. So in fact, if you look at this kind of an exposed layer of plasma, because of the huge amount of the SiOH present, there is always a molecular reorientation, and the surface is a very dynamic surface so therefore what we have typically observed as is that the cracks are responsible again for shooting up the long chain and the short chain oligomers which are there in the bulk of the material, and after a while you see that the contact angle kind of relaxes back to the normal, and it becomes more hydrophobic with time as you leave it alone after a plasma exposure. So these kind of studies have been done in lieu of what was represented in the last two slides. So I think I would like to conclude here this particular module in the interest of time, but we have other things on board, particularly related to the additive processes, which I would like to highlight in the next module, and I will also summarize on to the various regimes of the pressure based etching that I have already described in great details in this module. Thank you so much for attending to this module. Thank you.